Hello, welcome to In 5 Minutes. We have done with the fixed biasing and the self biasing. Next type is the voltage divider bias. Similar to the voltage divider biasing of BJT, you have R1, R2, RD, RS. Now which channel can say, depending on the arrow, P to N, forward bias current will flow from P towards N, so it is N channel JFET. Now which type of configuration you can say, look at the input. Input is applied to, can say this is your gate, this is your source, and this is your drain. Input is applied to the gate and output we are taking from the drain. So which terminal is remaining, that is common, so we can say it is common source configuration. Right, now starting with the analysis, what we do for the DC analysis, we remove AC sources and open circuit capacitors. When you are open circuiting, this entire part will go out of the circuit, this entire part will go out of the circuit, so you are left with only R1, R2, RD, RS and VDD. First what we'll do, we'll try to solve this circuit, which is potential divider biasing. Coming to the potential divider biasing, what we can write from this, since Ig is 0 ampere, right? What we can say, current through R1 equals to current through R2. That means no current goes over here. Whatever you have current flows into R2. There is no current in R2. So what I can say, Vg can be written as R2 upon R1 plus R2 into VDD. This is by, you can say, potential divider rule. You got Vg as R2 upon R1 plus R2 into VDD. Now this we have reduced the circuit and we have found Vg, right? Now our main aim was to find the gate voltage Vg, which is applied to the further JFET. Now the circuit would be like this. You have R2, R1. Now when you apply KVL in this loop, so what you can say, applying KVL to gate source loop, what will be the equation? Vg, we are living with a positive sign, minus Vgs, we are living with negative sign, minus Vrs, since we are living with a negative sign, equals to 0. So what I can write, Vgs equals to Vg minus Vrs. This Vg is taking on the other side, Vg minus Vrs. Now what we can say from the circuit, I can write Vrs as Id into Rs. So when I substitute this Vrs, Id into Rs in the above equation, what I will get, Vgs equals to Vg minus Id into Rs. So this equation we got for Vgs, right? Again, which can be simplified and can be written as Vgs equals to, that is plus Vg, which can be modified, and you will get it as minus IDRs plus Vg. Call it as equation number 2. Now we can say these two equations both are one and the same, just writing way is the different. So what you can say, both are for the straight line with decreasing slope, but origin now is not a point in the plotting of the line. That means we can say it is not starting from the origin, it has shifted to some point because of this plus Vg. Anywhere on the horizontal axis what we have, so we need to find the points. Now we are using the same equation. What I can say is, on the x-axis what you have, Vgs and Id, milliampere and volt. On x-axis I have my y coordinate to be 0, that means Id will be 0 on the x-axis. So what I can say, on horizontal axis Id equals to 0. When I substitute this condition in the above equation, what I will get, Vgs equals to Vg. For what condition? My Id to be 0 milliamps. So I have got one point, that is my Vgs is Vg for my Id to be 0. Now Vg is a positive value. Now this is the point, my Id is 0 and I am getting Vgs as Vg. So this is the point what I have got. Now what we can say, for the other point, at any point on the vertical axis what we can have, on vertical axis we have Vgs to be 0, that is this axis. So when you substitute Vgs 0 equation again, what you will get, 0 equals to Vg minus IDRs, or you can directly substitute in this equation Vgs as 0, you will get Vg minus Id into Rs. So what will be your Vg? Your Vg will be Id into Rs, but you want the value of Id on the y-axis, therefore I can write Id equals to Vg upon Rs for Vgs equals to 0. So I can say this is the another condition what I have got.